This is group 25, solving problem 9.64, which gives us a frame with a fixed supported A, an 800-pound horizontal load acting on the vertical member, a 600-pound vertical load acting on the horizontal member, and a 1,200-pound-foot moment at the free end, point C. It's given that in this problem, EI is constant, and the unknown to be solved for is the horizontal displacement of point C due to the bending moment. Now we're going to use the method of virtual work for this problem, which gives us that 1 times the displacement, which is point C, the horizontal displacement of point C in this problem, equals the integral from 0 to L of the moment in the members due to the virtual loads times the moment in the members due to the real loads over EI. First, we're going to solve for the moment in the members due to the virtual loads. So we apply a virtual load of unit magnitude in the direction of the horizontal displacement, which is a 1 pound horizontal load at point C, which gives us a reaction of 10 pound-feet at A. Now we need to solve for the internal moments, and because of the 800-pound force, the moments will be different in the two sections of the vertical and obviously the horizontal members. So the three internal moment equations we have are M1, which is the horizontal member, equals 0. M2, which is from point A to 5 feet, 5 feet directly above point A, equals to 10 minus x2, with x2 starting at point A, and M3, which starts at 5 feet above point A to the horizontal member, is equal to 5 minus x3, where x3 starts 5 feet above point A. So now that we have the virtual moments, we're going to solve for the real moments, or the moments due to the real loading. The external loads, 800 pounds, 600 pounds, and the 1,200 pound-foot moment give us reactions at A. The moment is equal to 8,800 pound-feet. A reaction in the x direction, AX equals 600 pounds. And a reaction in the y direction, AY equals 800 pounds. Now these external reactions give us sufficient information so that we can now solve for the internal moments. Now, like we did with the virtual system, the moments in the real system have to be solved separately from 0 to 5, from 5 to 10, and in the horizontal number. So the internal moment in the horizontal member equals 600x plus 1,200 pound-feet. The internal moment in the bottom half of the vertical member gives us 8,800 minus 800 x2. And in the top half of the vertical member, the internal moment is simply 4,800 600 pound-feet for the entire top half. So now that we have the internal moments caused by the real loads and the internal moments caused by the virtual loads, we can plug them into our equation for the virtual work, and we can finally get a value. So because we have three different moment equations, we have to break up the problem into three different integrals. So the displacement C is equal to the integral from 0 to 6 of the internal moment of the horizontal beam, which is 0. So 0 times the internal moment due to the real loads, which is 600 x plus 1200 all over EI plus the integral from 0 to 5 starting from point A of the internal moment caused by the virtual loads, which is 10 minus x2, times the internal moment caused by the real loads, which is 8800 minus 800 x2, all over EI. Plus integral from 0 to 5, starting 5 feet from A, so from 0 to 5, of the internal moment caused by the virtual loads, which is 5 minus x, times the internal moment caused by the real loads, 4,800 pound-feet, all over EI. So combining these and integrating them gives us that the displacement at C equals, factoring out EI, 1 over EI, $8,800x minus 16,800 x squared over 2 plus 800 x3 over 3, evaluating from 0 to 5. Plus 24,000 x minus 4,800 x squared over 2, evaluating from 0 to 5. This portion is from the top half, this portion from the bottom half. The vertical, or the horizontal number, since it was multiplied by 0, is simply 0, integral of 0 to 0. So plugging in 5 for x for both of these, we get delta C is equal to 32,333. I'm sorry, 323,333